I am going to go back and revisit this problem that we were in the middle of when the bell rang today. So here we are, we're using an approximation, and what we said in class about natural log of 1 plus x is that we actually could come up with this very quickly because we know that 1 over 1 plus x could be considered a geometric series. A is 1, r is negative x, and this then is going to become 1 minus x plus x squared minus x to the third, and on and on and on. Because of our restrictions, because this is a geometric series, we know that r has got to be sandwiched between negative 1 and 1, so x itself is sandwiched between negative 1 and 1. So this is our interval of convergence. And then if we were going to take the antiderivative of both sides, we would end up with ln 1 plus x is equal to x minus 1/2 x squared plus 1/3 x to the third minus 1/4 x to the fourth, and so on and so on and so on. So that's exactly what we are given, except we're only using two terms. Now, we're looking for the maximum error that we could have if x is some value within this interval. So let's think about how bad it can be. We know this is tangent at x is equal to 0. So at x is equal to 0, we just get a true statement. And the further we get away from that, the worse it gets. So let's pick the worst case scenario. Let's pick x as far away as we can. Let's try x equal to 0.1. So we're saying that ln of 1.1 should in fact be 0.1 minus 1/2 0.1 squared plus 1/3 0.1 to the third, and so on. But we are just using the first two terms. Now, one way we could look at this is we could notice that this is an alternating series. So the error, the amount that we should be off, should be our next term. And if we call this our error and we just plug it into our calculator, what I get for that is what I get for this is 0.0003 repeating. So that's our alternating series error. And if we actually calculate ln 1.1, and these two terms are actual error, ends up being 0.00031, I believe, is what I get. Okay, now that's fine, but in fact, we are trying to do the what we call the Lagrange error, right? The Taylor remainder. So let's look at this a little bit differently. So this is alternating series, but let's look at what we know about this Lagrange error. What we know is that we're stopping here at degree 2. So my error I'm going to call r sub 2. Right, so this is the remainder after we've gotten to a power of 2. Now what we know about r sub 2 of x, this was defined as saying this is going to be less than or equal to some m, some upper bound, over, in this case we're going to have 3 factorial, and we're going to have x minus 0 cubed. And again, we're looking for as bad as this could be. So the value I'm going to plug in for x is going to be the big one that's going to give me the biggest value here possible. So here, I'm going to plug in 0.1 for x. And m, if you remember what we know about m, is that m has got to be greater than or equal to our third derivative at some value in this interval. Some value in this interval between -1 and 0.1. And where we were in class was we knew that our third derivative of x was going to give us, let me look over here, we have 2 over 1 plus x to the third. And again, to anticipate the worst that it could be, we want to pick the x that's going to make this as big as possible. So let's let our denominator be as small as possible. This needs to be as big as possible. So let's let x equal to be negative 0.1. So what we're saying is that this third derivative, the worst it can be, whatever on that interval, is going to be 2 over 0.9 to the third. So let's let that be equal to m. Right, the biggest that this third derivative can be on that interval. Okay, so here we have the remainder is going to be less than or equal to, we're going to have 2 over 0.9 to the third. The whole thing is over 3 factorial. We're going to plug in 0.1 for x. So this is as big as possible. M, we know, has got to be greater than the worst possible scenario. And then we have that 3 factorial. And we can simplify this kind of a lot. 2 over 3 factorial, that's 1/3. This, that we have both things raised to the third, so that's 1/9 to the third. So what I get for this is, 4.572 times 10 to the -4th. And keep in mind our actual error was 0.00031, which definitely falls within the range of this. One thing to notice is that if your maximum value of that third derivative had been at x is equal to 0, our error for the Taylor would have been exactly the same as the error that we had for the alternating series, because keep in mind, our third term in an alternating series is really 1 over 3 factorial. We have our third derivative at 0, and then we have x to the third, right? So there's our third derivative again. There's our 3 factorial again. There's our x to the third. The only catch here was that our maximum value for this was not at 0.